Hi, thanks for joining me today. I'm going to be going over problem 3 from week 1 of the Invariant Summer Puzzle Competition. If you don't know what this is, I'll leave a link in the description below to the Facebook page of the Invariants where you can find out more details about the competition. Anyway, this is the problem we have for today. It's a limit and integral problem and it looks very, very scary. We have the limit as n goes to infinity of the integral from 0 to 2 pi of x cubed log of x multiplied by cosine of sine of nx plus cosine squared of nx, all divided by sine of nx times sine of nx plus 1 dx. If you want to have a go at trying to evaluate this limit integral problem, pause the video now and give it a go for yourself, and I'm going to jump straight into the solution. Okay, so the first thing I'm going to say about this solution is that it's quite long. It involves a lot of different steps. Some of the steps are really interesting and some of them are less so. So I'm going to focus on the interesting steps to the solution just for the purposes of the length of the video. I don't want to make it too long. And the steps in between, I'll leave as homework exercises for yourself to go through the details and connect the dots. But hopefully I'll just provide brief explanations of how you get from step A to step B. Anyway, I've written the problem we have in the top corner here in this little box, and instead of writing log of x, I've written L of x, and instead of cosine of sine, I've written C and S. And to solve this problem, the first step is we're going to use a lemma. And now, depending on the length of this video, once I filmed it, I'll either provide a proof to this lemma at the end of this video, or provide a proof in a separate video. And if so, I'll leave a link for that video in the description below. Anyway, what is this lemma? We have a function g from the reals to the reals, which is continuous and periodic with period t. And we also have a function f from 0t to the reals, which is continuous. The lemma then says that the limit as n goes to infinity of the integral from 0 to t of f of x times g of nx dx is going to be equal to 1 over t times the integral from 0 to t of f of x dx times the integral from 0 to t of g of x dx. So this is what the lemma says, and of course we want to use this to help us evaluate this guy here. Well, if we just let f of x equal x cubed times log x and g of x be equal to cosine of sine of x plus cosine squared of x, all divided by sine of x times sine of x plus 1, then we've got something very similar here to the setup we have in the lemma. But we've just got to check a few things. Firstly, is g real to real? Yep. Is it continuous? Yep. Does it have period t? Yep. T here is just going to be 2 pi, so cool. G is fine. Now, is f from 0 to t real and continuous? Well, technically no, because if we look at 0, when we plug in 0, we're going to get log of 0, which is not nice, but you can just go ahead and compute the limit as x goes to 0 from the positive side of this guy here is going to be equal to 0, because this guy here goes to 0 much faster than this guy here goes to infinity. So this guy kind of outweighs this guy going to infinity. So the limit as x goes to 0 of this guy here is just 0, so we can in fact just make this function a continuous function by just insisting that f is 0 at x equals 0 as well. So we don't need to worry too much about this endpoint here. So f from 0 to t to the reals is continuous, and yeah, it's very clearly continuous. So now we can just go ahead and use the lemma. So we've got the limit, if we call this limit here that we're working with, we'll call it L, is going to be equal to, by this lemma, 1 over t, so 1 over 2 pi, times the integral from 0 to 2 pi of f of x dx, so x cubed log x dx, multiplied by the integral from 0 to t of this guy here, cosine of sine of x plus cosine squared of x, all divided by sine of x plus 1 dx, like so. So that's all our lemma is telling us, that we've got 1 over 2 pi times this integral here. But it's quite nice because now we've gotten rid of the x cubed log x from this kind of trigonometric mess. And now this guy here, x cubed log x, is just a standard integral. You can go ahead and compute it using integration by parts, but hopefully for most of you that's a pretty standard exercise. If you're not convinced or you want to have a full proof, just go through the details yourself. It is just integration by parts, but this integral here just equals pi to the 4 times, I've written it down here, 4 log 2 pi minus 1. Okay, so L is equal to 1 over 2 pi times pi to the 4 log 2 pi minus 1 times this integral here. So hopefully it's clear to see that our main problem now is tackling this integral here. This is not supposed to be a t, it's supposed to be a 2 pi. But yeah, The next part is to work out what on earth this crazy looking integral here is, but before that, let me clean up the whiteboard. Okay, so we've proved that this limit integral that we're trying to compute is equal to this guy here, pi cubed over 2 times 4 log 2 pi minus 1 multiplied by the integral from 0 to 2 pi of cosine of sine of x plus cosine squared of x divided by sine of x times sine of x plus 1 dx. And as I say, we just want to focus on this last integral here. Now, again, this is kind of one of those boring, I don't want to say boring, less interesting steps, should we say, going from this guy here to this guy here. It involves a lot of writing, and as you can tell, there's not loads of space to be able to write loads of no's. So just going from this guy here, writing this integral, which I'm just going to call I for now. So this integral here is just I, and you want to work out what I is. We can see that it's equal to 4 times the integral from 0 to pi over 2 now of cosine of x plus sine squared of x divided by cosine of x times sine of cosine of x plus 1 dx. And the way you get from this guy here to this guy here, as I say, is just a bit of computation. What you want to do is split this integral into 0 to pi over 2 to pi, pi to 3 pi over 2, and 3 pi over 2 to 2 pi, and then just do some u substitutions like x equals pi over 2 minus u, and then bring them all down to the interval 0 pi over 2, use your trigonometric identities, and it will bring you down to this guy here. You've got a little 4 here as well. So I is equal to 4 times this guy here. The next thing we're going to do is just a u substitution. So we're going to have u is equal to cosine of x. So that means that du is just going to be minus sine of x dx. So if we just plug that into this guy here, we get that I is equal to 4 times the integral now. Well, when x is 0, u is going to be cosine of 0, which is 1. And when x is pi over 2, we're going to get cosine of pi over 2, which is 0. So 4 times the integral from 1 to 0 of cosine of x. So cosine of u plus sine squared of u, which is just going to be 1 minus u squared, because cosine squared plus sine squared is 1. So sine squared of x is 1 minus cos squared of x, so 1 minus u squared. And that's divided by cosine of x, so u, multiplied by sine of u plus 1. And then dx is just minus sine of x dx. So that's going to be minus, which I'll bring out the front, minus here, sine of x, which is just going to be the square root of 1 minus u squared. So it's going to be 1 over square root of 1 minus u squared du. Because dx is going to be equal to minus 1 over square root of 1 minus u squared du. And I guess it's important to notice that we don't have to worry about a plus or minus here because we're working over the interval 0 pi over 2 like so. Now we can use this minus sign here to flip the limits of integration. So this minus sign we can get rid of and put this as the integral from 0 to 1 of this guy here. So cosine of u plus 1 minus u squared all over u times sine of u plus 1. I'll just put that in brackets and then multiplied by the square root of 1 minus u squared du. And now this here still looks like a very complicated integral, and it is. And the way we want to evaluate this is by doing some substitutions. Now, this is another one of those long steps where there's just a lot of writing. So what I'm going to do is write down the main steps, and then I'll let you go through by pen and paper, go through the details yourselves. But we're going to do some substitutions here. So we're going to use one substitution. We're going to introduce variables p and q. P is going to be equal to 1 plus u sine of u, and q is going to be equal to u plus sine of u. So two seemingly arbitrary choices for p and q, but hopefully, it kind of makes sense that we want one of these guys to be this thing in brackets here, this guy here, because otherwise this thing is going to be horrible to deal with. And then if we differentiate q, we're going to get 1 plus cosine of u, which is similar to what we have on the top as well. Anyway, we have these variables p and q which I've introduced, and the main things you want to consider are p squared minus q squared. So I'll let you just go through the algebra and see what that guy there is equal to in terms of u. You want to consider that guy, and you also want to consider what is p dq minus q dp. And the reason you want to consider this is this guy here perhaps looks familiar if you've seen the quotient rule before. This is kind of the numerator of what you'd get on the quotient rule. But yeah, so these are the things you want to consider, and then what you'll get is the integral, I'll just write it as an indefinite integral for now, of c of u plus 1 minus u squared all over u s of u plus 1 times the square root of 1 minus u squared du. You go through, this is going to be equal to the integral of p dq minus q dp all over p times the square root of p squared minus q squared. And this guy here, what's that going to be equal to? Well, as I said, this top thing here, p dq minus q dp, is very similar to the quotient rule. So this is actually going to be equal to the integral of p squared all divided by p times the square root of p squared minus q squared times d of q over p, like so. So this integral we have here, which is the exact same thing here except in indefinite form, is equal to this guy here, and this guy here is equal to this guy here. And the reason we get this kind of p squared term on the top is, if you remember, if you think of the quotient rule, dq dp is going to be, or sorry, dq over p is going to be p times dq minus q times dp, all divided by p squared. And because we don't have a p squared in the denominator here, we add one to the numerator to cancel it out. And then we've still got this p times square root of p squared minus q squared, like so. So we have that this indefinite integral is equals to this indefinite integral here. And of course, this p squared, one of the p's will cancel with the p on the denominator as well, like so. And now we can use this to help us evaluate this guy here. But I guess the next step is to do another substitution, because q over p is a bit ugly. We want to have just one kind of variable there, so we'll just introduce another variable r equals q over p, and once we plug that in, this will kind of simplify down even further, and then we'll just get a standard integral, which we can then just write the antiderivative for, and then plug it back into this guy here. Anyway, let me clean up the whiteboard, and we'll continue. Okay, so we have that this integral here is 4 times this definite integral here, and the indefinite version, this guy here, we showed is equal to this guy here. And straight away we can simplify this. If we factor out a p squared from the square root in the denominator, it's going to come out to be a p, which will cancel with the p at the top. And what we're left with is the integral of 1 over the square root of 1 minus q squared over p squared d q over p. And then we can just say r equals q over p. And this guy here just equals the integral of 1 over the square root of 1 minus r squared dr. And this, of course, is just inverse sine or arc sine of r plus an arbitrary constant, because it's an indefinite integral. Now, this, of course, is r. R is q over p, and q and p are given there. So this is just inverse sine of u plus sine u, all divided by 1 plus u sine u, like so, plus c. And of course, this is just this guy here, which is what we have here. So let's plug in 1 and 0. When I plug in 1 to this guy here, I get inverse sine of 1 plus sine of 1 divided by 1 plus sine of 1. And of course, that's going to cancel to give me 1. So inverse sine of 1 is, of course, pi over 2. So this thing here is pi over 2 minus, when I plug in 0, I get inverse sine of 0 plus 0 divided by 1. So inverse sine of 0, which is 0. So this is equal to 4 times pi over 2 minus 0, which is 4 times pi over 2, which of course is just equal to 2 pi, like so. So thankfully, we've managed to get this integral here just equals a nice number 2 pi, and we can go ahead and just plug that in. So I get that the limit, this guy here, which I think we called L earlier, is equal to 2 pi times what we have here. And of course, the 2 is going to cancel with that 2, and the pi will make that pi to the 4 multiplied by 4 log 2 pi minus 1, like so. And that there is our final answer. That is the final number that, if we were to compute this integral and then compute the limit, we would get this number here, which is insane. And yeah, this has been a very long problem with a lot of steps, as I said. Hopefully you've managed to follow along. I don't think I'll prove the lemma in this video here, because this is probably already too long. So I will prove that in a separate video and leave a link for that in the description below. Anyway, I hope you have enjoyed this problem. Do check out the other solutions I make for the other problems. And if this is your first time here at the channel, thanks for watching this video. And if you are new, do consider subscribing as well. Anyway, thanks for watching. I'll catch you in the next one. Have a great day.